In this lecture, we will cover the basics of raster data management. So to begin with, the concept of storing raster data, it's a flat binary format, and there is metadata that is contained in a text file. The raster data are stored as a flat byte stream in a binary file. The text file that you will use when working with your NV manual is our NV header files. It has the same file name as a binary file, and it has a .hdr extension. So for instance, if the file name is biomass, the header file will be biomass.hdr. So raster data is comprised of pixels, and we see here a representation of 3 bands, just named band 1, 2, and 3, and it is organized in columns that go vertically and in rows that go horizontally. And so rasters are multiple band images that are represented by a combination of spatial position, and this is a combination of pixel number and line number and band. So this example here is showing the columns and the rows, and there is a single pixel in the bottom left that is shaded blue, and the digital number values are shown in the lower right hand corner. For simplicity, not all digital number values are shown, but each of those squares or pixels would have a digital number affiliated with it. Electromagnetic energy incident on a detector is converted to an electrical signal, and then this is digitized. In this quantization process, the relationship between the input signal and the output signal is generally represented by the S-curve that you see here. On the x-axis, we have a region that's unsaturated, we have a dynamic range, and we have a saturated area, and this represents the input, and the y value is the output. And this is a characteristic curve for a signal. When we talk about interleave type, we're referring to NV image files, and the NV image format is a flat binary raster file with an accompanying ASCII2 header file. The data are stored as a binary stream of bytes in one of the following 3 formats, and this is referred to as interleave type: band sequential, abbreviated BSQ, band interleave by pixel, abbreviated BIP, and band interleaved by line, abbreviated BIL. So we'll go over the definitions of these 3 types. First, I'm going to go through the definitions, and then I will show you a diagram of images to help reinforce the concept. So band sequential, BSQ, it's the simplest format. Each line of data is followed immediately by the next line in the same spectral band. This is optional for spatial access of any part of a single spectral band. Band interleaved by pixel, or BIP, it stores the first pixel for all the bands in sequential order, followed by the second pixel for all the bands, followed by the third pixel for all the bands, and so forth, interleaved up to the number of pixels. This provides optimum performance for spectral access of the image data. Band interleaved by line, or BIL, stores the first line of the first band, followed by the first line of the second band, followed by the first line of the third band, etc. Subsequent lines for each band are interleaved in similar fashion. It provides a compromise in performance between the first 2 mentioned types, BSQ and BIP, and it compromises spatial and spectral processing and is the recommended file format for most NV processing tasks. The NV raster format does not support 64-bit integer signed or unsigned data types. So here is a representation of the definitions that we just covered. So you can see the order of BSQ 1 through 9 in the red, and then below that 1 through 9 in the green, and then 1 through 9 in the blue. Contrast that to BIL, where the lines go 1, 2, 3, and then for RGB and then 456 RGB, and then 789 RGB. And then band interleaved pixel by pixel is the last representation here, and you can see that the top row is all ones, the next row is 2 on down. So this is a representation of how the data is organized with these different interleaves. BSQ is stored sequentially in the order of the pixel columns, so the pixel values of one band can be read at once. With BIP, the byte stream where the pixel values are stored in order of the band first, followed by order columns and lines. This is the fastest access to the full spectral profile of a single pixel, capturing the range of values that were collected in each different band. BIL interleave is a compromise between BSQ and BIL. The pixel values are stored in order of its column, band, and row, or line. This is advantageous for applications that require the full spectral information of a complete image line. We talked about radiometric resolution, and we're going to cover again radiometric characteristics of image data. So you can see here that information in a digital format is contained in a digitized image, and it's expressed by bits, which stands for binary digit per pixel per channel. And this example on the right is showing 8 bits that are grouped as a byte. So for computer processing, the unit of byte is 8 bits, and it has an integer value of 0 to 255. This is 2 to the 8th power. And so there are 256 gray levels. We go to 255 because we start counting at 0, not at 1. This is very convenient for computer processing. So in remote sensing, the quantization level is normally 6, 8, or 10 bits, or 1 or 2 bytes. And you can see a representative quantization level here for Landsat, SPOT, NOAA, AVHRR, and the SAR sensors. So radiometric corrections are necessary because we actually don't have an ideal Earth observation system. If we had a perfect system, the spectroradiometer that accurately measures energy levels reflected by Earth's surface would give us very, very specific and accurate data. But in reality, the sunlight that illuminates objects passes through the atmosphere and does not interact with all objects at the same angle. So you can see by the diagram here that sunlight is going to interact with dust, and this causes diffuse radiation. There are also gases in our environment and water vapor. So ozone gases, carbon dioxide, and water vapor are also going to scatter or cause the radiation to be diffused. And so radiometric correction is necessary. And the effects due to sensor sensitivity is called vignetting. And for sun angle and topography corrections, we use sunspot and and shading. And then finally, with atmospheric correction, we have to account for absorption and scattering within Earth's atmosphere. So to cover vignetting first, radiometric correction of effects due to sensor sensitivity is the definition of vignetting. An optical sensor uses a lens, and there's a fringe area in the corner that will be darker when compared with the central area. So in the case of electro-optical sensors, measured calibration data between irradiance and the sensor output signal can be used for radiometric correction. When we consider sun angle and topography, so first let's think about sunspot. The solar radiation will be reflected diffusely onto ground surface, which results in lighter areas in an image. A sunspot plus vignetting effects can be corrected by estimating a shading curve. This is determined by Fourier analysis to extract a low frequency component. With shading, The shading effect that is due to topographic relief can be corrected using the angle between the solar radiation direction and the normal vector to the ground surface. So this image up here is showing an original image and then the result after applying radiometric correction, and the representation below is the estimated shading curve for each of those pixels. And then finally, with atmospheric correction, there are various effects that cause absorption and scattering of solar radiation. Reflected or emitted radiation from an object and path radiance, also known as atmospheric scattering, should be corrected for. So atmospheric correction is a major issue in visible or near infrared remote sensing because the presence of the atmosphere is always influencing how that radiation is traveling from the ground to the sensor. So the radiation that reaches a sensor can be determined by the parameters L max, L min, and DN range. And these are known for each sensor manufacturer or operator. And this information will be found in the metadata file for your satellite imagery. Here is just a diagram representing the different components of the atmosphere that need to be corrected for. So starting at the top hand left, we have our top of the atmosphere irradiance, and this is a measurement of how much sun energy is coming into our atmosphere. Then we have surface irradiance, and you can see by the yellow lines that there is scattering in many places within the atmosphere. We have emitted long wave radiation, which is represented by wiggly lines. And then in the circles, we have gases, aerosols, clouds, atmospheric properties, and rainfall that all need to be accounted for. So solar radiation is absorbed or scattered by the atmosphere during transmission to the ground surface. At the ground surface, it's reflected or emitted from the target. It is also absorbed or scattered by the atmosphere before it reaches the sensors. The ground surface receives not only the direct solar radiation, but also skylight, which is represented in B. And skylight is scattered radiation from the atmosphere. And so you can all probably think of some days the light is brighter than on other days, and this is a reaction or a reflection of how much scattering is happening. A sensor receives direct reflected or emitted radiation from a target, and also the scattered radiation from a target. So these diagrams here are showing you the various atmospheric effects that can happen. Again, in a perfect world, we would have the conditions shown in A, where the sun energy would interact with Earth and then bounce to the sensor. But that's not reality, and so we have different variations that are shown in B, skylight, C, path radiance, D, scattering, and then E, multiple reflections. So these are all things that do happen in our atmosphere to solar radiation. So here is an example of an atmospheric correction. The scattered radiation from the atmosphere, called path radiance, has been corrected for using a digital image processing system. Three main areas of atmospheric correction. So there's a method that uses the radiative transfer equation, and then in B there's a method with ground truth data, and then C I'll talk about other methods. So going back up to the top, with the radiative transfer equation, an approximate solution is usually determined for the radiative transfer equation. So an aerosol is density, and it's visible, it affects the visible and near infrared region, and water vapor density affects many areas, in particular the thermal infrared region, and these should be estimated. Because these values cannot be determined from image data, a rigorous solution cannot be used. With ground truth data, there are data sets that accompany the remotely sensed image that are collected at the time of data acquisition, and those targets with known or measured reflectance will be identified in the image. This is made by the comparison between the known value of the target and the image data, which is your output signal. However, this method can only be applied to the specific site with targets or a specific season. And then finally, there are special sensors that will measure aerosol density or water vapor density, and these are utilized with imaging sensors for atmospheric correction. An example is the NOAA satellite. It has an imaging sensor of AVHRR, which stands for Advanced Very High Resolution Radiometer, but also HIRS, which is High Resolution Infrared Radiometer Sounder, and those are used for atmospheric correction. So I'd like for you on your own to explore atmospheric correction, and there are 2 YouTube videos that I want to assign, and if you click on the graphic below, it will navigate you to those videos. Please start with part 1 and conclude with part 2. Go ahead and pause this lecture and watch the iGet concept modules that discuss the digital number to the top of the atmosphere reflectance for OLI and TRS sensors. So here is an atmospheric correction example, and this is a LED APS atmospheric correction. So we have top of the atmosphere reflection in a composite of bands 321 for the Landsat 7 ETM plus image of San Francisco. That's shown in A in the top, and in B it has been corrected for surface reflectance composite. So you can see the difference before and after correction. There are geometric distortions and there are errors in a satellite's positioning on its orbit, and the fact that the Earth is turning on its axis as the image is being recorded creates distortions. There are also effects of relief, and so you can think of relief as the 3-dimensional aspect of the Earth. And this is amplified even more by the fact that some satellites take oblique or sideways images. So geometric corrections are necessary, and satellites have sophisticated onboard systems to record very slight movements that affect the satellite. This information is used mainly to correct the satellite's position when necessary, but it can also be used to correct the images geometrically. When we talk about image correction, the producers of satellite images generally propose applying the most elementary corrections based on the satellite's known information. With spot images, it's possible to buy geometrically uncorrected images or level 1A images. A large number of users work with images in which the distortions have been corrected systematically, and these are called level 1B images. And these corrections can be made without any special knowledge of the terrain or in situ data collection. The accuracy of locations in these spot images is on the order of 500 meters. So a little bit about the difference between accurate and precise. So you can see in this image above that in the first set of circles and black dots that it's very accurate. In other words, the data points are very close together, and it is also very precise if we are considering the actual value to be the center of those bullseyes. In the next one, it's not accurate, but it's very precise because the data points are still very close together and it is off center quite a bit. In the third example, we have accurate but not precise. So the 4 dots are close to the center bullseye, but we don't have a tight fit for the circles. And then finally, the last example, it's neither accurate nor precise. So to improve the precision of the correction, reference points that are known as ground control points must be available, and these can be identified on a topographical map or collected in the field by a GPS unit. Spot images that have been corrected in this way are accurate to approximately 50 meters, and the data that they contain may be presented on a given map projection. The images are superimposable on a map. There's also a distortion by parallaxes. So the concept of a parallax, if we consider a mountainous area, there's considerable distortion that is caused by the parallaxes generated by the terrain, especially when the images were recorded from an oblique or side view. On the graph shown here, the left point A corresponds to the position of the mountain peak, whereas the point B is where the mountain peak is seen by the satellite. So the distance between A and B is known as the parallax, and that's the difference in elevation. In a digital model of terrain, a computer file is giving the physical elevation of each pixel in the image. So as a rule of thumb, it is considered that satellite images can be corrected under ideal conditions in a way that the distortions do not exceed the size of a pixel. So for example, 10 meters for a spot P image. But if the truth be told, these ideal conditions are rarely seen. So some more things that can cause geometric distortion if we consider the movement of the aircraft. The first diagram that is showing the label idealized would be an aircraft flying over the Earth in the direction of the black arrow below with a very stable platform. In reality, we have roll, which is side to side, we have pitch, which is up and down, and then yaw, which is also side to side but in a horizontal direction. And so all of these things will cause geometric distortion in an image. And there's a difference between the actual image coordinates and the ideal image coordinates, which would be projected theoretically with an ideal sensor under ideal conditions. Filtering is an operation that is designed to improve images' readability and or extract information from them. So in this example, we have a red polygon that is drawn around 3 theoretical pixels, and the filter is applied, and what it does is it actually takes an average of all of the values and applies a mathematical operation to it. And so the filter analyzes those 9 pixels and then gives a resultant value of 6. So we have 2 9s and 7 5s. Using the algebraic equation shown here, you come up with a result of 5.89, and this is rounded up to 6. So the same mobile window has been applied to the 3 bands R, G, and B in this example for the image on the left. The filtered result to the right shows that many fine details, the strands of the hair, the parts of the eyelashes, etc., have disappeared, and the image appears more blurred. So this type of filtering that eliminates small details or ones that with high spatial frequencies is also called low pass filtering. So filters can be used to reinforce the perception of an image's sharpness, and in this example of a spot image taken in Brussels, the original image to the left was improved upon by applying a filter to enhance local contrast. The right-hand image clearly looks sharper, even though the processing did not add any information. You're not changing the data, you're just changing the way it is displayed visually. So with contrast, what you're doing is you're allowing the display system to break each primitive color into 256 degrees of intensity. An image that uses the entire intensity scale, that is digital number values from 0 to 255, has excellent contrast. And this is because the color range will extend from black to white and include fully saturated colors. In contrast, an image that has narrow range of numerical values will lack contrast. It will appear more grayish. And so looking at the images below with their histograms that accompany them, you can see that the best contrast is represented by image B or histogram F, and it's making use of the full spectrum of the digital numbers. Whereas image C is more grayish, it is not as sharp black and white, and it has a narrower range of digital images. So with contrasting, most digital image display systems allow one to break each primitive color into 256 degrees of intensity. An image that uses this entire intensity scale contains values coded from 0 to 255, and it has excellent contrast again. For the color range would extend from black to white and include fully saturated colors. So you can see here that an image with a narrow range of numerical values shown in the top representation of a rocket satellite taking off from the Earth, it has a more grayish look than the one on the bottom, and the one on the bottom is making use of more of the 0 to 255 values. The contrast is better. You can see sharper colors, you can see details on the rocket, you can see details in the clouds that are not visible in the image above. So the top image is poorly contrasted, and the graphs show that there are only a few dozen values in the red and green spectral bands, and then even fewer in the blue band. It also shows that the blue and green values are higher overall than the red values. You can see that by the height of the histogram. The bottom image is the result of a constant spread function, and you can see the histograms on the bottom. It's like you were taking both ends of the data and stretching it out and matching it to the capability of the pixel values, 0 to 255. So this does involve changing the numerical values of the original image according to a linear function. And there is an equation here, and you're doing that for all three components, R, G, and B, and make use of all possible values. So why do we use contrast function? It's almost always applied to remote sensing images that are analyzed, because Earth observing satellite sensors are set to be able to record very different lighting conditions. And we have deserts and ice flows, which are very highly reflective areas on Earth, very bright. And we also have equatorial rainforests and dark oceans. And the equatorial rainforests appear, because of the thick vegetation, as dark, and they register dark digital numbers as well. So when we talk about color images with remote sensing, you want to think about, are they true colors or false colors? So a digital image recorded by a digital camera is displayed on a computer screen in a logical manner. So in other words, the display system red channel is associated with the camera's red channel, the green channel with the camera's green channel, and so on. The resulting image is a faithful copy of what you would see with your naked eye. And a red colored object in this type of true image would appear red, a green colored object would appear green, etc. But we can apply the tools of our software using ENVI or ArcGIS, and in remote sensing systems it is possible to detect and record parts of the electromagnetic spectrum that cannot be detected by the naked eye. So for example, we can display the infrared band choosing a color gun from our computer monitor. To visualize this information, we pair up display colors R, G, and B with spectral bands in the observation system that do not necessarily correspond to them. And in so doing, we create colored composites that are sometimes called false color images. This is an example of rocks from the moon, and they do not appear this color in reality, but this is a composition of digital numbers that was created by an analyst. So if we want to analyze three component data, we have red, green, and blue pixel colors that range from 0 to 255. This can generate more than 16 million different colors. The human eye is a very powerful analytical tool, for it can compare different objects' colors, but it can also analyze the colors' juxtaposition, the object's shapes and sizes, etc. And these possibilities are the basis of remote sensing image photo interpretation techniques. Here are some composite possibilities. The first one combines information from bands 321 for the TM satellite, and this is a natural color. And for the same TM satellite, 432 gives an infrared false color. And for the bands 354, it gives a color composite. So using the 7 spectral bands of the thematic mapper sensor, here are 3 images of southeastern Brussels and its suburbs. So false color infrared composites are particularly effective for rendering and analyzing remote sensing data. This technique associates the sensor's near infrared red and green bands with the colors red, green, and blue on your screen. Vegetation offers the advantage of having essentially the same properties as the color infrared photographs with which photo interpreters have been familiar for years.